We're now going to be working with the logarithmic function. And logarithmic function states for x greater than 0, b greater than 0, b not equal to 1, that y equal log base b of x is equivalent to b to the y equals x. So if I'm taking a look of a logarithm, you have the log, you have the base of the log, you have what you're taking the log of that does have a name. It's called the argument. And then you have what the log is equal to. And this is really an exponent. Didn't have room to write exponent. It's really an exponent. So essentially that's what this is saying. It's equivalent to the base raised to the y power is equal to x. So the log that we're going to be working with primarily is natural log. Natural log is a log that has a base of e. There's e again. And it's called ln x. The biggest thing we're going to be doing, one of the biggest things we're going to be doing, is going to be moving from notation, log notation to exponential notation to log. If I wanted to change this to an log notation. Don't do that very often, by the way. This is, if you think about a logarithm, the logarithm, remember, has a base, and it has the thing that you're taking the logarithm of, and you're looking at the result. So you're going to be looking at the base is the base, and the base is a base, so the base is a. So this says that you have log, the base is a, you're going to be taking 2.1, and you're going to be returning it to 3. The log is an exponent. The log is an exponent. What we do most of the time is taking it from log notation to exponential. So this would take 3 to the negative 2, come back through the equal sign, 1 over 9. Now remember, natural log is base e, so this is log base e of x equals 4. So e to the 4 equals, come back through, x. Now let's take a look at this domain thing, and it says, definition of the log, what is the domain? Well, there is a relationship between exponentials and logs. And this is what the relationship is, and you saw this in college algebra. So what the exponential function does, it takes x values to y values. So that would say y equals a to the x. Now what the logarithm does, in this case it would be log base a. Well, log base a picks up y values and returns them to x values. So that the exponential takes it from the domain to the range, y value. The log brings it back. Now here's one of the more important things. I'm going to draw this again. Is that if the exponential function takes the domain to the range, what's here in the domain is all real numbers. What's in the range are only numbers from 0 to infinity. So that means that the logarithm takes numbers between 0 and infinity and returns it to something which is all real numbers. So that means that the log has a domain restriction. And that restriction is what you're taking the log of, which we called the argument, must be greater than 0. Because you're pulling numbers that are greater than that are greater than 0, taking it back to all real numbers. So what would the domain of the natural log of x plus 1 be? Well, the argument must be greater than 0. Argument is x minus 1, must be greater than 0, or x must be greater than 1. Now that means if I were doing derivatives on the number line, that my number line starts and does not include 1, so it's 1 to infinity. Now I'm going to do 2 pages on 1 because this is not a very big page. And how do I graph these guys? Well, the easiest way to graph this is to rewrite as essentially x is equal to, so 2 to the y is equal to x, 2 to the y power. Now, what does that mean? I'm going to put in y values, and I'm going to get out x values. Now the domain, if I'm looking at the domain, x has to be positive. What I'm taking the logarithm of has to be positive. And the range is all real numbers. So that I can't put 0 in because I can't take the log of 0. 0 is not in the domain. I'm going to put in 1/2. I'm going to put in 1, 2, and 3 and see what, whoops, I'm sorry. Maybe putting in y values. Sorry about that. So I need to put in y values. Now, if I'm putting in y values, y can be any real number. So I can use any real number I like. So -2, -1, 0, 1, and 2. This would be 2 to the y. 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So if I look at x being 1/4, I'm at -2. If I look at x equal 1/2, it's -1. At 1, it's 0. At 2, it's 1. At 4, it's 2. And so this is what he looks like. He has a VA at x equals 0. Because x and y are flipped. So if you notice I'm dealing with the exponential, it's the other way around. Exponential has all real numbers as his domain, and y greater than 0 is his range. But you're flipping everything. He has an HA at y equals 0, so the logarithm is going to have a VA at x equals 0. Same thing's going to be true here, except this is the log base e of x. So that's going to be equal to y. E to the y equals x. -2, -1, 0, 1, and 2. Well, e to the -2, e to the -1, e to the 0, e to the 1, e to the 2. So e to the negative 2, I've done this before, e to the negative 2 is 0.1. And then e to the negative 1 is 0.4. E to the 0 is 1. E to the 1 is 2.7. So the one e that I didn't get is an e squared. And he's 7.4. So 0.1 is negative 2. 0.4 is negative 1. 1 is 0. 2.7 is 1. And 7's all the way out here, which would be 2. He looks very similar to log base 2. So he has a domain. Of course, x is positive. He has a range of all real numbers. And he has a VA at x equals 0.